Hi everyone. Thanks for taking a look at my first talk here at NCNGT. Pretty excited to give it. So before we get started, I guess I should give a thanks to our organizers, of course, especially our organizers of this smaller, I forget what the smaller groups are called, but Ursula and Men, thanks for this invitation and for putting this together. So it should be pretty fun. So the first talk, I'll give two talks, and the first of these is called Splitting Symplectic Fillings, as you see here. So we hope to, we'll recall the definition of a symplectic filling, and then we hope to develop a technique for analyzing the symplectic fillings of a given contact manifold. I would love it if you would butt in with questions, but that feels unlikely. Okay, so recall that many symplectic manifolds with boundary, of course, will endow their boundaries with a contact structure. This is one of the many relationships between symplectic and contact geometry. So what I have in mind in particular is an exact symplectic manifold. So we have some manifold with boundary that has a symplectic form, and we demand that this symplectic form be exact, hence the name. Once it's exact, we could define this Liouville vector field via the pairing of our two form with this one form, the symplectic potential, which we will call a Liouville form. The existence of this vector field is, of course, automatic from non-degeneracy, but the requirement we're imposing here is that it point transversely out of the boundary of our symplectic manifold. So if we have such a thing, then the kernel of this one form lambda, when restricted to the boundary, this is a contact structure on the boundary. So we'll call such a thing an exact filling, and we'll say that it's an exact filling of a given contact manifold MC if that contact manifold is contactomorphic to the boundary. Okay, so you've probably seen these before, but just in case you haven't, here's an example. We can consider a ball in Euclidean space of even dimension. And here's this one form that I think of as standard. It's not the tautological Liouville form that you may be familiar with, but it's a pretty standard looking Liouville form. And if you take its derivative, you'll find that you have the standard symplectic form on R2n. So that means this ball is a symplectic manifold with boundary. There's then a pretty easy computation to show that with this symplectic potential, the Liouville vector field will be this radial vector field here. And that's, of course, going to point transversely out of the boundary, giving us an exact symplectic filling. So in 2 dimensions, we have the very boring picture of a disk with some sort of radial Liouville vector field. The disk carries this symplectic form, and the one form, when restricted to the boundary, gives us a contact form. So then, in fact, this will give us a contact structure on odd dimensional spheres, and in fact, it's the same contact structure as the standard one, however you've chosen to define the standard contact structure on the sphere. Okay, so there's an example, just a silly, easy example to have in mind. So a very natural question then is, what if I start with the boundary? What if I start with a contact manifold? Can I enumerate its fillings? For this talk, we'll focus exclusively on exact fillings, but there are other types you might want to classify. So we're going to call this a filling problem for obvious reasons, and that will be the focus of our 2 talks, is to think about filling problems for tight contact manifolds of dimension 3. So our 2 goals have 2 talks. They go together, but the goal for talk 1 will be to develop some sort of technique for reducing a given filling problem, one we're interested in, to the same problem. You still want to classify, say, exact fillings for some other contact manifold. And hopefully this other contact manifold, maybe its fillings are already classified, or maybe the filling problem is just more tractable there. And then we can sort of bootstrap a solution here back to a solution to our original problem. So that's the goal for this first talk that you're currently experiencing. Talk 2 will be to use this technique that we developed to complete the solution of the filling problem for all lens spaces. So all of the standard lens spaces saw their filling problem solved over a decade ago by Liska. And what we'll discuss is how this technique that we develop in talk 1 can be used to reduce all of the non-standard lens spaces to just standard lens space filling problems. All right, so let's start thinking about this reduction of the filling problem. So we can go back into history a little bit and look at the result of Eliashberg from 30 years ago, where Eliashberg showed that if we have a contact manifold obtained from some other, probably disconnected contact manifold via connected sum, then every, strong or exact, I really didn't mean to include the word strong there, but every exact symplectic filling of this new contact manifold just looks like a filling of the old one with a one handle attached. So morally, we have some contact manifold in which we are interested, and it looks like a connected sum of two other contact manifolds. And so what Eliashberg's result tells us is that this is the same thing as just two separate fillings, the fillings of the two parties to our to our connected sum. And so, this attaching of a one handle is really just a boundary connected sum. And so this is, of course, a very helpful procedure for classification, because, for instance, if you can classify all of the S1 cross S2 fillings, then you can just take all the boundary connected sums of those fillings to get a list of the connected sum fillings, fillings of connected sums of S1 cross S2. So another way to state this same result is to say that if our contact manifold admits a convex sphere, S2, which is what you would see where you have performed your connected sum. So if somehow our contact manifolds are now two-dimensional surfaces, then where you've performed the connected sum, you're going to see a convex sphere. Then Eliashberg tells us we can remove a Weinstein one handle from any of those exact fillings, and we get a new filling of some new, hopefully simpler contact manifold. Okay, so how does Eliashberg prove this? Well, very roughly, he introduced this technique called filling by holomorphic disks. So if we have our contact manifold of interest to us, here in red, and we have some filling, we can think about the completion of that filling so that everything over here on the right just looks like the symplectization of our contact manifold. And this convex sphere, since it sits inside of a fillable contact manifold, well, that means it sits inside of a tight contact manifold, and there's really only one characteristic foliation it can have, morally speaking. So I'm thinking of this in terms of dividing curves, even though Eliashberg's result predates that sort of thing. So there's essentially only one characteristic foliation this thing can have, and it splits the sphere into two disks, which by some sort of lies we can treat as disjoint disks in our contact manifold. So each of these disks will lift to a holomorphic curve in the symplectization end of our filling, our completed filling. And then we can make some sort of argument based on the limited characteristic foliation here that these families of holomorphic curves in fact sweep out sort of a one parameter family of disks from our filling. So hence the filling by holomorphic disks. Well, if we take this one parameter family of disks and we consider some neighborhood of it in our filling, that neighborhood just looks like a Weinstein one handle. So it can be removed from the filling, and we're left with a new exact filling of a new contact manifold. And then you just need to investigate the effect of removing a one handle, and you'll notice, oh, it corresponds to sort of undoing a connected sum. And so this disconnected green contact manifold here is the contact manifold from which we would obtain MC by connected sum. So there's a very quick and rough explanation of Eliashberg's argument that isn't really doing it justice, but hopefully will suffice. This leads to a new question. What if we have a convex surface with positive genus instead of just a sphere? Can we run the same sort of argument? Can we look at some, this isn't supposed to be sigma g, but it's supposed to be maybe the positive region or negative region of sigma g, and attempt to sweep that out, sweep out an annulus or sweep out some sort of planar shape with multiple boundary components instead of a disk. And then we would get over here, instead of a one handle, a symplectic handle modeled on that region, which maybe I don't want to get the details of right now. So the answer is yes for some convex surfaces. It turns out because we don't have as much control over the characteristic foliations that appear once we have genus, just having a convex surface isn't enough. But if we have a convex surface which is mixed in some sense, so the statement given here is just for genus 1, that satisfies some sort of additional geometric criteria, then the answer is yes. So there are a lot of words on this slide, but the point is, you start with some filling of some contact manifold, you produce a new filling of some contact manifold. This new filling looks like your old one minus a round one handle. And a round one handle is just a one handle followed by a two handle. The middle statement is easily deduced from Minke's proof. So this is a result of Michael Minke from about 3 years ago. The middle statement points out that, well, before we knew that if we removed a one handle from our filling, this corresponded to undoing a connected sum. It's not as straightforward when we are removing round one handles. This, instead of just undoing a connected sum, we are splitting our manifold open along the torus. And there are various possible slopes along which that can happen. So we'll have to delay the explanation of this middle statement just a bit. Okay, so the answer is yes for genus 1. Some of the things I've already said are noticed on this page of remarks, where a convex torus satisfying additional geometric criteria will be a mixed torus, and those criteria are chosen precisely to make Eliashberg's strategy work. The second statement gives us a list of possible contact manifolds which result from this decomposition, and then a round one handle is just a one handle followed by a two handle. So what about genus that's still higher? The answer to that is yes as well. But once again, we have geometric criteria that must be satisfied, which I maybe don't want to get into right now. We're just going to focus on the genus 1 case today, because the proofs are essentially the same, and the genus 1 case will suffice for our applications. Okay. So in the remainder of this talk, which unfortunately seems to be only about 10 minutes, we will attempt to define mixed tori, or at least give some idea of what they are, and understand why they allow Eliashberg's strategy to work, and then try to define that middle conclusion from the theorem, which talks about splitting a contact manifold along a mixed torus. Okay, so to define mixed tori, we first need to recall what a basic slice is. We're not really going to recall it, we're just going to make some vague statements about basic slices. So a basic slice is a thickened torus with some contact structure. It's a tight contact structure. These were defined by Honda a little over 20 years ago in order to classify tight contact structures on lens spaces and torus bundles and other three manifolds where you might expect to find thickened tori. Some of the salient points about them are that, well, basic slices have some correspondence with bypasses, which is another word, I'm not actually going to define. But the point here is that we understand the RAID dynamics. We understand the contact geometry in general pretty well within a basic slice. And then if we have two boundary slopes, by which I mean the slopes of the dividing curves of the boundaries of this thickened torus. If these boundary slopes admit a basic slice, then they admit precisely two. One of them is positive and one of them is negative. So with that very loose recollection of what a basic slice is, we can say that an embedded torus in a contact manifold is called a mixed torus if you can write it as sandwiched between two basic slices. So what we want to see here is T. This whole neighborhood looks like T2 plus 0, 2. Maybe on the left we have a negative basic slice, and on the right we have a positive basic slice. So then this thing in the middle will be a mixed torus. So why is that the definition? Well, we choose that as the definition because it gives us a lot of control over the RAID orbits that appear in a neighborhood of T. So that's precisely what's going to make Eliashberg's strategy work when proving this result, this JSJ decomposition. Because now, when we attempt to run this filling argument, just as before, we can lift the two annuli that appear in our torus. So we have a mixed torus, so that means we have dividing curves which split our torus into two annuli. Each of these annuli on top and on bottom will lift to a holomorphic curve in the symplectization, and we want to analyze sort of some one parameter family of holomorphic curves and hope that they sweep out a round one handle. Okay, so they do, and I'll reproduce that sort of ugly torus we had before. And this is like kind of a nonsense diagram here that's supposed to explain what's going on. So here's our mixed torus. This E1 and E2, these are the two dividing curves that appear on our torus. These are elliptic RAID orbits. And the nice thing about being sandwiched between basic slices is that we can precisely identify all of the other nearby RAID orbits, or at least all of the ones whose action is in the range that we might need to consider. So we start with some lift of our positive region. So this green curve here is supposed to represent a J-holomorphic annulus with ends at E1 and E2. So that's something up here. And we ask how this might degenerate. And because of positivity of intersections and because of things like the existence of holomorphic curves along with limits at these other RAID orbits, we're able to argue that the only possible degenerations here are into two-level holomorphic buildings connecting to these other RAID orbits that appear. And so up to, again, some amount of lying, this family here connects maybe our positive version of the holomorphic curve to our negative version using this bottom piece, and allows us to sweep out some family of holomorphic curves and remove a one handle. So this is all very hand-wavy, and I'll be happy to discuss some more details in the office hours. But the basic idea is that we define mixed tori so that they have these neighborhoods where we know what the Rabe orbits are, or at least the interesting ones, and we can control what happens as we fill by holomorphic disks. Okay, so maybe more interesting to us for our next talk is what it means to split a contact manifold along a mixed torus. So we only have maybe 4 or so minutes left, but I think that'll actually be enough to get our heads around what's going on. So remember, a mixed torus is sandwiched between 2 basic slices. And these basic slices have some slopes for their, once we identify T with R2 mod Z2, the slopes of the dividing curves may be given, I think in our example in talk 2, they'll be given by -2, -3, and -10/3. But by reviewing this identification here, by re-identifying T with R2 mod Z2, we can always normalize this embedding so that the mixed torus itself, T, has dividing curves of slope infinity. The side opposite the negative basic slice has slope -1, and then the only piece we can't control is what will happen on the far side of the positive basic slice. So this would be our S2 in the statement of the theorem. But once we normalize these 2 pieces, there's some S2 here. Okay, so as we said, every mixed torus admits some normalized embedding by re-identifying our torus. So once we have that identification of T with R2 mod Z2, and we choose some integer S, we can split open our contact manifold along the torus. We will then have 2 boundary torus components along which we can glue in a solid torus. So our new thing, this split open manifold, will be a solid torus glued along one boundary component plus a solid torus glued along the other boundary component. And this integer S that we've chosen will allow us to define the maps that we use to glue in the solid tori. We'll glue these in so that the meridian of the solid torus has slope S. And again, this all depends on some identification of the torus with R2 mod Z2. So then we can make this a contact manifold by saying on M minus the torus, the contact structure is unchanged. On the solid tori, well, this contact structure that exists on M minus T gives us a characteristic foliation along the boundary of the solid torus. And Honda says there's a unique tight contact structure with that characteristic foliation. So there's some unique extension of C across these 2 solid tori. Some unique one that will be tight on each of these solid tori. So very finally, we point out that when we apply the symplectic JSJ decomposition, by construction, this produces a filling of some contact manifold, which is obtained by splitting along T with some slope S. However, we can check, and this is just sort of an investigation of the contact planes as they traverse this journey from one solid torus across M minus T to the other solid torus. In order for that M sub S prime to be tight, we must have S, the slope with which we split, sitting between 0 and S2 minus 1, where S2 minus 1 is this one slope of a normalized embedding that we can't control. So this gives us the second statement of the theorem, that the slope must be bounded in this region. So in our next talk, we'll try to apply this enumeration that's given here to lens space fillings. So we can talk about what happens when you split a lens space along the mixed torus with one of these given slopes. So I do apologize for rushing somewhat through the notion of splitting along a mixed torus, but I'm happy to answer any and all questions via Discord or office hours. All right, thanks once again for coming.